También si me pudieras después pasar el link de YouTube, Cristi, te lo agradecería.
Sí, claro que sí. Listo, estamos en vivo.
Ok, vamos a dar un minutito y empezamos. Okay, we are live now, but I'll just wait 1 minute and we'll start.
Okay, so you should see my presentation now.
I see your presentation. That's
okay, perfect.
Okay, I think we're going to start. So it is a great pleasure for me to introduce Professor Philippe Bouyer from the Institute of TIC. Professor Philippe Bouyer obtained his PhD at the Castler-Brussels laboratory of the École Normale Supérieure in 1995, working with Christophe Salomon. He continued with a postdoc at Stanford University, where he developed, under the direction of Mark Kasevich, the first experiments of inertial sensors, like the ones that he will show today, that are based on matter waves. He then moved to CNRS and the Institute of TIC, working with Bose-Einstein condensates to do atom lasers and Anderson localization with cold atoms with Alan Aspe. He has been the director of the Photonics Numerical and Nanosciences Laboratory, LP2N, since its creation, where they do research in multiple topics, including ultra-cold atom quantum simulators and the development of atomic interferometers for testing general relativity in microgravity or for detecting gravity fields and gravitational waves with an underground antenna. More recently, together with Arnaud Landreguin and Bruno Desruelles, he founded the company MuQuants, which produces integrated quantum solutions. In particular, they produced the best portable gravimeters, commercial portable gravimeters nowadays. And it is then a great pleasure that he accepted our invitation, and having such a distinguished professor giving us a colloquium to us, it's a great pleasure. And he will tell us about quantum sensors with matter wave from the lab to the field. And the last thing before I turn the microphone over, remember that you can put your questions via YouTube on the chat, and I will relay these questions to Professor Bouyer as the talk goes on. Thank you very much for accepting the invitation.
Well, thank you very much for the introduction, and thank you very much for giving me this opportunity to present the work we are doing in Bordeaux. So Bordeaux is in France. It's the southwest of France. It's the evening now there. So it's a special honor to be invited, and I would have loved to come to Mexico. I've never been there, and hopefully in the next months we'll have the opportunity to travel again, and I will be very happy to visit your institute. I just learned that the institute has its birthday, 65th birthday, so happy birthday, and I hope that you will enjoy this talk as a birthday cake for the day. So I will talk about quantum sensors, and in particular quantum sensors using ultra cold atoms, matter waves. And the research we've done was really starting with applications to fundamental physics and using these sensors in the lab, but I will show that we are now able actually to have portable sensors, or not so portable sensors, but really working in any kind of environment, from underground to space. And this is an example of an underground laboratory, which I will present later. So why do we speak about quantum sensors? Mostly because it relates to the hot topic today. Hot topic, which is quantum technologies. The quantum technologies applies to a very vast level of applications, going from computing to communication and sensing. And in our case, the quantum physics that is at the core of our quantum technology or the quantum sensors is the superposition principle. The fact that a quantum system, when it will evolve from an initial state, psi A in this case, to a final state, psi phi, can actually use many different paths or many different evolution paths to go from A to B, or from the initial state to the final state. And what quantum mechanics tells you is if you have many possibilities or many ways to evolve, then the probability to make this evolution has to be not the sum of the different probabilities, but the sum of the amplitude, and then you compute the probabilities. And because you are considering the amplitude and not the probabilities anymore, then quantum mechanics tells you that you can have interferences between the different possibility of evolution. And this interference can lead to actually an enhancement or an hindrance of the possibility to evolve. So that's a general aspect of quantum mechanics. And there is another general aspect, which is actually more than one century old, is the fact that if you want to describe a particle in quantum mechanics, you can actually choose whether you will describe it as a particle. In this case, you use energy and momentum, which is the mass times the velocity, to describe the evolution of this particle, or you can describe it as a wave. And in this case, you will use frequency or wavelength, which tells you actually how this ondulation, this wave, is changing with length in terms of wavelength, or in time in terms of frequency. And what quantum mechanics told us, at the beginning, it was introduced by Albert Einstein with the photon, and then it was generalized by a French scientist, Louis de Broglie, for any type of particle, is that you have a duality between matter waves, or between waves and particle, and you can actually define the wave property of matter by introducing a de Broglie wavelength, which is the analog of the photonics wavelength, and which is inversely proportional to the momentum I introduced before. So from that concept, you actually realize that even in analogy with optics, you can, using matter and matter wave, engineer systems where the evolution can lead to interference patterns. And so how do we build this interference pattern, or this interferometer that we want to use for our quantum sensor? What we need is to basically define a couple of different evolution paths that our system, in this case atoms or matter wave associated with the atoms, will actually follow to go from the input of your interferometer, which is the equivalent of psi I here, to the output of your interferometer, which is the final state, psi f, for quantum mechanics. And if we want to build two paths, what we need to do is, in analogy with light, to split the matter wave in two different directions using an atomic beam splitter, and then to be sure that these two paths will cross again, so we can use mirrors in order to bend the trajectories, and then a last beam splitter that will mix the two paths, or that will mix the two parts of the same matter wave, which is in a coherent superposition. Doing that and looking at the output of the interferometer, so you have two output ports in this case, the one that could look at as coming from the path 2 and the one that could look as coming from the path 1, you will see a modulation of the probability for the matter wave to exit in one or the other output port, this modulation being proportional to the cosine of the phase difference between the path 1 and the path 2. So this is this picture here, that these are actual data. Each point represents an experiment where we monitor the number of atoms by changing the phase difference between the two paths, and we see that we indeed have this sinusoidal modulation corresponding to an interferometer. So how do we build this atomic beam splitter? So there are many ways you can, and I don't give you here a history of atom optics and atom interferometry. There are many ways, starting from the fact that you can actually send some matter through some slits, like you would do with light, and you can look at the diffraction from the slits at the output. In our case, we prefer to use a virtual slit, which is basically using light in order to modulate this probability and to make this beam splitter. And there is a very simple analog for that. It's the fact is, if you consider that you have two different states, one ground state and one excited state, each corresponding, if I go back to, for example, the black direction here, the black trajectory or the green trajectory, then light will couple these two states and will induce an oscillation between the two states as if you have two-level atoms and that you excite with an electromagnetic field. This oscillation is called the Rabi oscillation, and you can control this Rabi oscillation extremely precisely by changing the intensity of your excitation field, which in this case is the light you're using. So of course, in our case, it's a little bit more complex. It's not a two-level atoms. We select two different levels, and in order to actually induce this oscillation between the two levels, we use, for instance, Raman transitions or Bragg spectroscopy. But the basic principle is the same. We have two states, one corresponding to a state which is not changed by the light, and the other one which is changed by the light. It is changed by the light with different aspects. The first aspect is you have a difference of energy, and the energy you put with the light will actually help you to change the states. But because we are using light, there are photons in the light. Photons carry momentum, which means that when the atoms will absorb the light, they will not only absorb the energy to change state, but they will also absorb the momentum of the photon. And momentum conservation tells you that in this case, one state will actually have a different velocity from the other one, which means that an atom or matter waves entering this beam splitter will exit in two different paths with two different directions. And that's the core idea of matter wave manipulation. We use the energy to connect two different states, and then we use the fact that because we photon carry momentum, these two states will actually fly apart from each other with different velocities. So using that, we can actually use a series of pulses. So we start with atoms, we cool them down. We cool them down to have a lower velocity, which means that the associated wavelengths would be larger. So the interference effect or the wave properties will be more obvious in this case. We remove the atoms that we don't like and we just keep the good ones. And then we apply a series of 3 pulses. And because we can control basically this Rabi oscillation I presented before, we can choose whether we stop halfway and then we have a beam splitter, one part which is not affected by the light and the other part which absorbs the photon and then is kicked by the photon itself. Then we can reverse the velocity and the trajectory by just telling the atoms in the excited state or the part in the excited state to go in the ground state and the part in the ground state to go in the excited state. And we apply the last beam splitter exactly the same way we applied the first one. What's nice with this technique is if we use different states with different energies, then we can really monitor the output of our interferometer by just looking at the associated states using just laser spectroscopy. And with that, and that's the first experiments that we performed almost 25 years ago now at Stanford University using two hyperfine state and Raman transition. And we can monitor each hyperfine state with a different type of laser, and we record that with fluorescence or with a camera, and we record the atomic fringes. So that's the key elements, and that's the key methods to build an atom interferometer. So now the question is, how can we how can we compute the phase difference in this interferometer, the phase difference between the two paths? So we go back to the basic of quantum mechanics in some sense. We say we have two paths, and then we really have to compute how the matter wave following the path, or how the quantum system following one path will be affected by that. One way to do it is based on Feynman path integrals. So we just look at the path, any possibilities of the path, but then we can really use the minimum path, the most probable path for it, and then we just have to integrate what we call the Lagrangian over this path, which is just everything which is affecting your quantum system. So what's affecting your quantum system? Something that happens during the pulse and something that happens between the pulses. So you need to compute the phase difference from the path using path integral for everything that happens when you don't do anything to the light. And for instance, in that case, you will see that if you have a gravitational field or if you have a rotation, you can have a phase shift which integrates over this just simply because you have a potential energy that will actually affect your system. But you also need to compute what's happening when you make a light pulse. And here what you found is when you actually manipulate the matter wave, not only you change the energy inside your atoms to change the level, you also affect the momentum, and you also imprint an information about the phase of the light at the position of the center of mass of your matter wave. So you have basically three effects of your laser interaction: energy, momentum, and phase. Energy changes the state, momentum makes the interferometer, and phase imprints basically the phase difference for your interferometer. The magic thing when you compute that in details is because in between the pulses, if you, for instance, want to measure gravity, then the trajectory will be bended by gravity. The actual phase effect from gravity itself, because the trajectory is already bended, is zero. And you can find a complete calculation in this reference, for instance, or in some other references from Claude Cohen-Tanucci who studied that some time ago now. So if I want to measure gravity, I want to make a gravimeter, for instance, I want to measure the phase that this inertial effect will put on my matter wave in the vertical direction. I simply apply a series of 3 pulses in the vertical direction. Then the atoms will be dropped into this beam. So this is a time space diagram now, time between the pulses, time t, for instance, in this example, space that goes down and increases while the time increases because the atom fall down. The trajectories are bending. There is no effect between the laser pulses, but you see that because the trajectory is bended, the position of the center of mass of the matter wave changes with time. And when you compute and you make an exact calculation of the phase difference at the output of the interferometer, you find out that your phase difference scales as 2 pi over lambda, which is the laser wavelengths used for the manipulation, times the acceleration you want to measure, times t squared. And it's basically the same formula if you're just considering that you are looking at the phase corresponding to the position of the matter wave in the light, and that you are measuring the distance between the first pulse, the initial position, and the last pulse, the last position, and you compare this distance with a reference distance, which is just the difference between 2 lobes of your standing wave, which is the laser wavelength. The distance here is gt squared, lambda is this distance, and this is completely analogous. So, and this first, I have to say, even if it looks very simple, it is exact at the first level. Of course, then you have many other parameters that, or many other terms that you need to compute if you want to be very precise. But at first order, this is an exact formula. The second thing is this simple picture I gives you lots of insight about the sensitivity, the accuracy, and what you need to make a very good gravimeter. First, the sensitivity. If you want to be sensitive, it means that you want the largest phase for the smallest gravity, for the smallest acceleration here, which tells you that in this case, you cannot really change lambda because it's related to the atoms you're using. You just need to increase the time. And if you increase the time, the distance increases as the square of the time. So you gain a lot by increasing the time. If you increase the time by a factor 10, you gain a factor 100 in sensitivity. The other point which is important is it tells you that in order to be accurate, you need to be sure that the phase you measure here corresponds to the acceleration you want to measure with the proper scale factor. And here, the scale factor is only 2 pi t squared over lambda. It only depends on the wavelengths of the light and the time. 2 parameters that you can control and know very well using atomic clocks or using very precise clocks and using laser stabilization, which means that the scale factor of a gravimeter using matter waves is extremely well known and extremely stable. So in that case, you can be very accurate and also long-term stable for the measurement. There will be no drift. And that's 2 aspects of the properties plus the sensitivity I mentioned before that are very important for this type of sensor. But last but not least, if you want to be very precise, and if you want to measure a distance with a ruler, a very precise ruler, even if the ruler is very, very precise, if the ruler is shaking, you cannot make a very good measurement. And that's another thing, is the key parameter or the key element to stabilize and to know and to control when you want to make a precision measurement is the light ruler or the light pulse you will actually use for this manipulation. The atoms themselves are a perfect inertial reference. They are perfectly in free fall in their vacuum chamber, and they are mostly not affected by anything. And so, and you will see that many tricks had to be developed in order to make this work in many type of different environments. So to conclude with that, just to give you an order of magnitude of what you can expect if you make a series of pulses with 1 second between the pulse, and if you have something like a million atoms to make your measurement, so a signal-to-noise ratio of 1,000, you find out that the minimum acceleration you can detect is 10 to the minus 10 meters per second squared. That's more than 3 orders of magnitude larger than the modulation of gravity induced by a tide. So it's very precise. This number corresponds to less than a millimeter of change of height if you want to measure gravity to compare with height. So this is extremely precise. So just as a takeaway message about why are we so excited with quantum sensors? Because they have 3 important properties, and they have these 3 important properties at once together with the same instrument. They can be sensitive. You can look at very tiny changes of acceleration or any type of number you want to measure. They are exact. When you measure something, you know that it is what you want to measure and not something which is biased, and they are long-term stable. And just to give you some example of application, when I'm speaking about sensitivity, I can, for example, apply it to gravity and say, if I'm very sensitive, I can look at tiny variations of gravity. And this can be, for example, induced by changes of density underground to detect water or underground resources with these variations. When I'm accurate, this is exactly what you want for a clock. When I want to measure 1 second, I want to be sure it's 1 second. And if I know that very well, I can then define the time at the second for hundreds of thousands and millions of years. And if I am very, very stable and I use it to measure acceleration, then if I use this acceleration to compute my position, because it's not drifting, I know where I am extremely precisely without the need of an external reference like a GPS. And that's these examples and these properties that have been driving basically lots of the research which is actually booming in this field nowadays. And this is also why we were motivated not only to pursue the research on that, but also to say, well, there is something to do with the commercial product. So I will not give you details about that, but just to say that 25 or 30 years after the first principle and the first demonstration in the lab, you can buy an atomic gravimeter. It looks like this, and the latest version are even more compact with that, and anybody can use it. I mean, you have some lasers and electronics in this box. You just almost need a control key to turn it on. You just need to plug a few cables. And then in this cylinder here, you have atoms, matter waves that are manipulated with light and measure gravity with extremely high precision at the level of about 10 to the minus 9 G, which is 1 microgal, which is the best measurement you can reach with the best instruments on the market so far. So from that experience and from the experience we built from that, we found out that there are many ways of using and exploiting these quantum sensors. And there are many ways with applications from very fundamental aspects of physics that I will present to applications. And there are also many ways to building sensors in any type of environment, not only a research lab. And we have examples now of experiments that we operate underground, under a mountain. I will talk about that, in space or in planes. And we also want to use that as a transportable systems for example, looking at underground resources or monitoring volcanoes, for instance. And this is the things we are doing with the commercial product. So I will now give you a few examples of what we are doing with respect to experiments we've been pursuing in Bordeaux. I will start with the underground experiment, which is the most fundamental aspects that we are trying to explore. Here, we don't only want to build one quantum sensor. We want to build a network of quantum sensors. We want to build them underground in order to get a very high sensitivity. So if we have a network of sensors, we can actually not only measure gravity, but we can also measure the variation of gravity with space, which is called the gravity gradient. And there are many applications for that in terms of geodesy applications and monitoring. But what motivation also for that was to detect gravitational waves. And just before I explain why we are so excited to use this quantum sensor for that, just to tell you, this is a national initiative so far, and it's also like connected at European level. Basically, we don't build it in Bordeaux because the mountains are not so far. It's the Pyrenees, further south, but there are no mountains in Bordeaux, only the ocean and the wine. But luckily, or I don't know if we should say luckily, but in France, France was one of the nuclear nations at some point, and we had some sites for nuclear weapons. They are decommissioned now, so this is the luckily part. And because they decommissioned this site, we could use it. And the site was ultra top secret, so it has to be buried underground. And this is one of the best places to build a high precision measurement. And it's in Rustrel in the southeast of France. And this is one picture of these big tunnels in which we are developing actually our quantum sensors. So why are we excited to not only use that for the geodesy, but also for gravitational wave physics? So just a brief recalling, we can observe gravitational waves essentially for very dramatic events of very massive objects like black holes or neutron star colliding together or merging together very, very, very far away from Earth. And because they are very big, they create a perturbation, a space-time perturbation of gravity, which is actually propagating in space. And because they are very, very far away, what we can detect on ground is a small variation of this, a super tiny variation. It's the space-time variation, which is called a space-time contraction, will actually change the time the light travels between two inertial references. And the way to detect that so far is by using a super precise interferometer in which the end cap mirrors of the interferometer are these inertial references. So there are mirrors that are suspended, and at a frequency higher than the suspension frequency, the mirrors can be considered as free-falling mirrors. And in this case, if there is a perturbation of space-time, they are basically following the geodesics, and you just measure the distance or the time the light takes to go from one mirror to the other, and this is your signature. And this is very efficient. It has been developed for many years, and now we are detecting black hole events, like many events per year. But there is a limitation to that systems. The problem is because you have this mirror, you need to hold it, you need to suspend it against gravity, and you need to isolate it from the noise, which means that you have some mechanical constraints that limits the sensitivity to these systems to frequencies of the order of 1 to 10 Hertz. Because to make this below that, the mechanical equation tells you that you will need to make a gigantic infrastructure, which is beyond the reach. So one solution is to go to space, and there is a project to build such an experiment in space. And another solution is to change the proof mass. And that's where the atoms start to play a role, because the atom is a perfect proof mass. Your atoms are free-falling objects. And the nice thing is, if you drop a mirror, then you break it. If you drop an atom, you just can recover another one and redo the experiment. So we can actually have perfectly free-falling objects, and we can interrogate the phase of the light with this perfectly free-falling object, which means that if there is a change of the time the light takes to go from one atom to the other one, then the phase will change, and our quantum sensor will basically detect this phase change as if there was a distance modulation for LIGO. But there is another advantage of atoms, is the fact that you can not only put one atom at one end of your laser and one atom at the other end, but you can put a string of atoms along the beam path, as shown here. And in this case, if there is a gravitational wave passing by, you will see that there is a contraction which is increasing as the time increases. But now, the problem of this sensor is at lower frequency. If you are on the ground, any type of mass movement coming from the clouds, coming from seismic activity, will actually give you also a signature that can look like a gravitational wave, except that because it's very close, it will have a spatial signature. And if you have more than 2 points, then you can use the spatial signature, and you can see, basically, in this case, the difference between a gravitational wave and a simple cloud or a simple earthquake close to your system. And that's basically what we want to demonstrate with the sensor we're developing here. So how can we do that? basically our idea is to build up a gigantic cavity as for LIGO, but then in this cavity we will launch atoms, and the light in the cavity will be used to build an atom interferometer. So the light will act as the beam splitter I presented before. And this is very challenging, and we want to build a very long cavity. And I don't have time to enter into the tiny details of what we are aiming here, but the goal is to detect gravitational wave, which means that you need to detect tiny changes of distance at the level of relative distance at the level of 10 to the minus 17. And that translates into gravity sensitivity lower than 10 to the minus 15. So it's super precise. It's beyond what we can do today. And to do that, we want to basically launch the atom in this long cavity. But if you make a long cavity, then you cannot really make a pulse. And that's a few things that we have to address in our approach. The cavity will give you lots of power, will give you a very nice phase reference, will give you a very nice laser mode. So all this is in favor of getting the super large sensitivity that we are trying to reach. But it will be very hard to make the proper beam size, and it will be very hard to make the proper pulse length. So maybe you would say then you will not succeed. But I just wanted to convey another aspect of atom-light interaction, is the fact that if you want to make the manipulation of the atoms with light, you can switch the light on and off. When it's off, nothing happens. When it's on, everything happens. But you can also switch the atom, and that's something we have basically studied. Is you can use a dressing light, so an additional laser beam that will change basically the internal structure of your atoms. It's called light shifts. If you put some light, then you can change the energy levels because of the coupling between this light field and the atoms. And by just changing that, you can actually tune or detune the effect of the light you want to use to manipulate. And this is something we've been studying, and this is a very promising aspect where the light in the cavity is always on. In this case, it's perfect. You stabilize it, you make it operating, and you just switch on and off, like you have an on-off switch using another light or using a magnetic field that will tell that when the atoms are exactly at the right position in your beam, then you tell the beam to interact with the atoms, or in order to tell the atom to interact with the beam, you create the beam splitter, your mirror, and then you make your atom interferometer. So these are all the aspects that we basically want to study in this very large interferometer, and it's basically a unique tool. There are a few ones that are under construction, one in the US, and one in China, and that's these unique tools that will be used to really push the sensitivity of these sensors beyond what we can do today, using all these tricks that I mentioned. So just to give you a brief overview of where we are, first we have a small prototype, small being only 10 meters. So this is in the lab in Bordeaux. And this is a picture of this. You see here the tube in which the light is traveling, and here you have one box in which you have all the things to make the cold atoms, launch them, and make the interferometer. And this is a typical interferometer fringes. So here we scan basically the fringes, or the probability to be at one or the other output of the interferometer, and we change the time between the pulses. So these are very short times, because this experiment is at very short scales, and we can, by just looking at this variation, shows that there is a tiny, so the phase actually increases quadratically, which shows that we are basically measuring effect of gravity because we tilt the beam a little bit. This is a prototype, and we're building the big thing, so in which we will have the light propagating over almost 200 meters and a few atom interferometers launch in between. And this is a picture of the cavities that are just finished, and a picture of the tubes that are being assembled here on the ground. And hopefully so COVID also delayed the installation, but hopefully by the end of the year there will be tubes there and there will be atom working. So that's it for gravitational wave detection. This is a very fundamental aspect, but basically also a unique instrument with sensitivities that can open new windows for geodesy. I will switch now to another topic that we are interested in, which is also addressing a very fundamental question. And this very fundamental question is actually a very important one that you usually ask your kids when they're young is what falls faster, a hammer or a feather? And usually people say a feather falls smaller, and you can laugh because in principle now everybody knows that there is an equivalence principle that tells you that any object falls at the same time, at the same speed, in the same gravitational field. But it was not so obvious because Aristotle actually believed that there was a difference. And it's only when Galileo introduced the principle of inertia and the famous experiment performed on the Pisa Tower, then actually we started to believe that there is an equivalence principle, and this equivalence principle is the cornerstone of general relativity. So we don't want to use a feather and a hammer. We want to use atoms, and we want to test this equivalence principle by using two different atoms of different mass and different composition, and showing that they fall at the same speed in the same gravitational field. And that's very nice with atoms because you can put two atoms nearly at the same place at an Angstrom level. You can put many atoms nearly at the same place, and you can use almost the same lasers to manipulate them. So you can have an atom interferometer with two different atoms in there that will actually measure the same quantity, gravity. And if there is a difference, it will tell us that the equivalence principle can be violated. And this actually is expected by some theory, complementary theory for general relativity, like superstring or quantum gravity, etc. So it's a very important topic. Of course, the goal is to reach a very high sensitivity. In our case, we've been focusing on two different atoms, rubidium and potassium, because the mass difference is a factor 2 and the wavelength is almost the same. So we can really build two interferometers, as shown on this graph, where we launch the cloud of atoms, superimposed atoms, in nearly the same interferometer. And the interferometers are not exactly happening at the same time because we want to keep basically the scale factor identical and the wavelengths being slightly different. K here is different, so we need a slight change of t squared here to get the same scale factor. So we perform this measurement, and what's nice here is because we perform two measurements at exactly the same time with exactly the same system, we have what we call common mode rejection. Any fluctuations that would limit the sensitivity of one measurement or the other can actually be ruled out by correlating the two measurements. And this is what you see in this example, for instance. Each measurement is basically flattening out, even if we try to average the measurement, where usually you expect when you average to increase your sensitivity. But now if you look at the differential measurement between potassium and rubidium, you actually find out that the more you wait for the measurement, actually the more measurements you do, the better is your sensitivity. And with our experiments, we were able to go down to something about 10 to the minus 8 in terms of sensitivity. The accuracy is a little bit less because the experiment was not designed for this type of measurement. And we are still looking at all the effects that can actually bias one measurement with respect to the other. But the goal of our experiment was really not to push the sensitivity at a low level on ground, but was to test this experiment with a view of using it in space. And for that, we basically put our experiment in a flying laboratory. So the flying laboratory is called the Zero-G Airbus, as you see on this picture. So it's a plane. It's actually, this plane is one of the former presidential plane of Angela Merkel from Germany. But it's not flying completely standard. As you see, it will actually describe parabolas. So it's a parabolic flight. And when you are at the top of the parabola, basically the plane is almost in free fall. So it describes the trajectory a ball would describe. So when you're inside, you're floating as if you were in space. As you see here, this is one of my former students. He's not sitting down, he's basically floating in space. And here you see some other postdoc of the experiment who is actually floating, and it's not, it's a real picture. So of course, you don't do that in real life because you get sick most of the time, but for the experiment, it's great. You can really try many things, but the environment is very demanding. It's very demanding because you have very strong vibrations, it's a plane, and very strong rotation because it's basically changing angle by 90 degrees in about 20 seconds. And these two effects are actually a very strong impact on how you can operate a quantum sensor. So the first thing is if you try to make a precision measurement with a ruler which is shaking, as I said before, you don't measure anything. And this is what's happening there. If you want to actually look at the output of your interferometer in time, so I'm just doing the experiment, and as I showed you before, if I do the experiment and I change the phase, I can see a very nice sinusoid like that, but here I just see a random distribution of points. Gee, it's not working. Actually, if I'm looking at this, like the distribution, the probability to find atoms at a certain level here, I recover a very nice curve. It's this kind of a Batman curve that we call it, with 2 ears there. Each ear corresponds to the maximum and the minimum of the sinusoidal here. So that tells you about the contrast of your interferometer. The width here tells you about the signal to noise ratio of your measurements. And because you know very well the scale factor, as I said before, basically you should be able to recover the signal because it's still hidden in this noise. So how can you do it? Why do we have this random distribution? Simply because there is so many vibrations in the plane that basically you're not sure where you are on the fringe. Maybe you're here, maybe you're here, maybe you're here, maybe you're there. And you cannot resolve a periodic signal if you don't have a definition of the periodicity which is good enough. So in order to do that, we actually have to know how the ruler is shaking. And we do that by putting an accelerometer, and we measure basically the acceleration of the mirror, which is used to define this ruler. And this is what you have here, the recording of the acceleration of the mirror. And when we correlate this plus this, then we can actually know where we are on the fringe. So the classical acceleration tells you you're here or here or here or there. And then from this knowledge, you can actually compute the real acceleration, and we were able to recover the black dots here are the measurement of the acceleration of the plane while the plane is flying with a hybrid classical plus quantum sensor for acceleration. And that was the first time it was actually performed in a plane. It's about like more than 10 years ago now. And since then, we actually knew that we can operate a very sensitive system in a very noisy environment by using this hybrid quantum plus classical approach. So there are still some problems that you need to solve. And one, which is basically not obvious, is the fact that your system is rotating. So what you have to imagine is that now we have the plane, which is rotating like that, and you want to measure towards the ground. So your axis of measurement is also rotating. But the atoms have also a small velocity because we launch them. And because you have a small velocity and you have a rotation, then you have a Coriolis effect. And this Coriolis effect is actually pulling the two trajectories apart, but in the perpendicular direction. So in the horizontal plane, which means that even if, when you look at the trajectories, even if you have the impression that they cross, they actually never cross anymore. I mean, they cross here in the vertical plane, but they never cross in the horizontal plane. And now the problem is, because we are trying to make interferences with matter wave, if this separation is too large, you won't see any contrast because your matter wave will not be coherent enough. So how can we define the coherence of a matter wave? Simply by cooling atoms. The cooler the atoms are, I told you before, it defines the de Broglie wavelengths, and it defines the level, in some sense, of wave behavior of the particle. But if you want to do that in a more accurate or a more mathematical way, it actually defines the coherence of your system. The cooler, the more coherent you are. And this is what we saw here. If we cool down atoms, rubidium was cooler than potassium, we find that we lose contrast much faster with a hot cold atom. I mean, they're hot in the sense that they were 10 microK and microkelvin, and rubidium was only 2 or 3. Still, in this case, because it's rotating so fast, because the atoms are still quite hot, 1 microkelvin in this case is very hot, then we lose contrast in a very short time, a few milliseconds, where we would like to actually achieve hundreds of milliseconds or more of interrogation time. So we need to sort this out. And of course, we cannot stop the plane to rotate because it needs to do this parabolic flight. So there are a couple of ways to do it. Either we can rotate the mirror in order to make the measurement, or we have to increase the coherent length. And to do that, we need to make the atoms colder. The way to do the atom colder is to push the laser cooling of atom beyond what can be done with standard cooling techniques, which means going from standard magneto-optical traps and cold atoms to Bose-Einstein condensate and ultra-cold atoms. And that requires lots of work. And we found out, we thought that the plane might not be the best place to really try to do that. So we built our own microgravity simulator. As you see here, we basically take an experiment on a small elevator and we launch the elevator, and then we keep the elevator go up and down as if we were launching it with a hand, like playing with a ball like that. So it's actually making a parabolic flight the same way the plane is doing. And during this time where it's up and down, it's in microgravity. So we can actually recreate the environment, not for 20 seconds, but for half a second. But the advantage of the experiment is we can make the experiment every 10 seconds, where we fly only once or twice a year. So in that experiment now, we trap the atoms, not only with the classical lasers, but we also trap the atoms is what we call a dipole trap. And I don't have time to explain into the details, but we cross laser beams and we focus them at the center of the chamber. And because they are focused, it's like an optical tweezer. The atoms will be actually trapped into this optical tweezer, and then we can apply very fancy cooling techniques for the specialists. We use a gray molasses that is using dark state, in the sense that when the atoms are excited by light, at some point they will fall into a state where they don't see the light anymore. And because they don't see the light anymore, they are not excited by the light. And because they're not excited by the light, they can be very, very cold. And with that, we can really put lots of atoms in the tiny volume here, only a few microns. And then we cool them down by a technique which is called evaporation. We remove the atoms with a higher energy. We just keep the atoms with very low energy. And this is a standard technique to achieve Bose-Einstein condensate. Again, because I want to show you the panorama of quantum sensor, I will not give you a dedicated lecture of how you make a Bose-Einstein condensate, just to give you what we are doing. So we cool down atoms. We lose atoms, but still we get atoms at very, very low temperature. Now we're not speaking about micro-Kelvin temperatures anymore. We're speaking about nano-Kelvin, tens of nano-Kelvin temperature. So orders of magnitude colder. Because they are much colder, they will actually expand much slower. So we can look at the expansion of the cloud. And because they are not falling down, we just take a tiny volume and we look whether the atoms stay in this tiny volume or not. If the atoms are falling down, they will not stay in this area. If the atoms are too hot, they will not stay as well, and we lose atoms, as you should see. If they are not falling down and they are very cold, then the atoms stay in exactly the same place for almost half a second of microgravity, as you saw here. In this example, we had atoms at about 100 nanokelvin, but we were able to go down to a few nanokelvin, so very, very cold atoms. And in this case, the current length is very, very large, and we can now start to actually work again on our atom interferometry, and that's some first picture. Now we can even take a picture of the matter wave here, and we can take a picture of the diffracted matter wave. See here the three lobes. That's the matter wave that have been actually diffracted by the light, and there are three lobes because in the way we apply it, there are some parts that go up, some parts that go down, and some parts that go forward in this way. It's called double diffraction, and we were able to record again very nice atomic fringes, as you see here. These fringes are done with super, super cold atoms in microgravity. So the very nice part of this studies is it showed us that we can actually do a lot of things, even in an environment which is not a laboratory. And this will be the last part of my talk, is now we can really think of the weirdest environment, the worst environment for a precision measurement, and still try to exploit the precision of quantum sensors. And one of the applications, which is very interesting, is navigation. Why is that? Usually when you want to navigate, which means you want to know where you're going or you want to know where you are, you rely on external sight. When you travel, you look where you're going. If you want to go through a door, you look where the door is, and then you keep sight on the door and you walk to the door. If you want to use radio navigation with a plane, you will use beacons and you will triangulate with these beacons in order to have a precise position. While you use a GPS, your beacons are satellites, and you do exactly the same. You refer your distance from the satellite, and if you have more than 2 or 3 satellites, then you can start really to compute your position with very high accuracy. Of course, if you don't have any view, you cannot actually get any information about your position. In that case, you need to rely on internal information. this is basically what you can do yourself. You can close your eyes and you can still walk for a while, and you will still keep going into the same direction. And it's not because you have the memory of the direction, it's because you have an inertial navigation system in your body, the internal ear, and you're integrating the information about this inertial system, acceleration and angular position or rotation. And from that, you actually have information about your position. But you will tell me that if you try to reach the door and you closing your eyes, there's a very high probability that you will basically hit the wall. It's because your inertial navigation system has a very strong bias. It's not very precise. And you compute your position, so you know more or less where you're going, but you don't have enough precision to reach the door. And this is basically exactly the same problem that will happen with super fancy inertial navigation system. Any bias will lead to a very large position error. In real life today, if you want, for example, to fly from Mexico to Paris, your plane will use inertial navigation references, but will need to actually recalibrate with GPS. Otherwise, it will never reach France without an external site. So you cannot rely only on internal references. So this is where we think we can apply a quantum sensor again. And in this case, we'll still apply the same technique as we used in the first experiment I showed in the plane. We'll use this hybrid approach. We will actually use a classical accelerometer, in this case, a classical inertial navigation system, and we'll use a quantum sensor. But in my previous example, I was basically using the classical accelerometer to get information about the quantum sensor. In that case, I will use the quantum sensor to basically recalibrate from time to time the classical inertial navigation system in order to actually know whether the measurement the classical system is doing drifted or did not drift. And this is basically what you do with GPS. And this is very classical hybrid approach. Classically with GPS, you have a hybrid approach with a navigation system, which is in this blue box here, and a GPS. And in our case, we replace the GPS with a 3-axis quantum navigation sensor. In our case, so far, we're just using a 3-axis accelerometer. We use the same approach using Kalman filtering and the coupling. And we were able to show that if you compare with a classical navigation system, that's the black line here, then using the recalibration with quantum system really reduces the drift, because the lower you are here, the better you are in accuracy. And this is exactly what we're trying to do. So it shows that you can actually rely on this comparison between a classical system and a quantum system to improve your navigation measurement. So just to show that we try to get this system fairly compact, and this is our very small 3-axis accelerometer here. It actually works on a platform where you can tilt it and it's still working. And it's still working because it's 3-axis. And I think it's the first time we are actually able to operate a quantum accelerometer in a moving platform, not knowing about the orientation with precision, because it's basically the quantum sensor which is measuring it. So we have 3-axis measurements. And as you see here, if you only rely on one axis, you can integrate. So you have ripples here. They come from the typical resonance of your sensor, like the time between the pulses and etc. But globally, you can actually really improve your measurement. And at some point, the 3-axis themselves start to drift because you don't have the knowledge of the orientation. But if you correlate them, and yet you keep on getting improvement in your measurement, showing that indeed, if you have a good knowledge of a 3-axis accelerometer, you can really get very, very good accuracy and long-term accuracy towards your system. So far, our 3-axis is just 3 times 1. So we are just like interrogating the atoms in one direction, interrogating the atom in the second one, and then the third one. But of course, the challenge would be, and this is something we really want to try in the future, to use the fact that quantum mechanics allows you to basically do everything. You just have to be innovative. So why not build not only a beam splitter in 1D, but a beam splitter in 3 dimensions, and then create a very complex superposition of a matter wave, which is now propagating in a 3 direction at once. And in this case, we can make some kind of a cube of a matter wave, so a cubic interferometer, cubic in the sense of it has the shape of a cube, and this actually can measure acceleration or rotation in every direction at once, and that's going to be a unique quantum systems that we are trying to develop now with our experiments. So with that, I will conclude. This is the general overview of some of the applications and some of the things we are trying to do in my group in Bordeaux. We have other projects that I did not mention, but really I think this flashes lots of potential applications and prospects and the exciting future for this quantum sensor. And we're so exciting that we are now building a local disruptive quantum center in order to push this technology even further in Bordeaux. And this is a nice picture of Bordeaux. This is a famous bridge. So it's not the Golden Gate Bridge, but it's something very similar that is from the Bordeaux area. And with that, I thank you very much for your attention.
Thank you very much for that fantastic talk. That was great. A lot of different aspects of gravity. That's impressive. So I remind everybody that you can put your questions on the chat. So let me pose a question from the chat. It says, with the technique that you show, where they use the distribution of population instead of the fringes itself, do you lose accuracy in the gravity measurements?
Okay. So if I understood the question well, so we are not actually looking at fringes. We are basically scanning the fringes with by just changing the phase of the interferometer. So actually, no, we don't lose accuracy. The fact is, because we are using not super cold atoms, you cannot really see the fringe because they are blurred altogether. And for that, you would need a much higher resolution, and we don't need to use a camera for that. So what's really happening now is we are averaging some fringes, but we have the accuracy of the phase difference between the two paths by just looking at the population difference. And it's basically a very nice way, and it's we don't lose any accuracy for that.
Okay, so another question. Do you have any opinions about what will happen with the measurements with antimatter?
Well, the equivalence principle should tell you that they would fall at the same speed as anything else, because so I guess antimatter will fall down as standard matter. Now there might be a small changes, and that's basically something related to the equivalence principle. If there is a parity violation at some level, that can actually lead to a change of gravity. This is a violation of the equivalence principle, and this has an impact on theory or the potential theories.
Okay, thank you very much. So related to the first question, increasing the number of measurements gives a better accuracy using the distribution technique, or it depends on how well it is defined the maximum of these distributions?
So it's a very interesting question. So to that respect, there are many aspects of the sensitivity. So maybe if I go back to one picture like this one, for instance. So the first aspect is if you have more atoms in your interferometer at one shot, or if you repeat the experiment many times, you will gain as the square root of the number of experiments. So each atom is one experiment. If I put 1 million atoms, I'm making 1 million experiments, I get a signal-to-noise ratio of the square root of that. If I repeat these experiments with 1 million atoms 100 times, then I also increase the sensitivity by the square root of 100, so which is a factor 10. Now, if I am the top of the fringe, I'm not very sensitive to any change of the thing. So usually it's like for clocks, I really want to operate on the slopes where the sensitivity of my sensor is the best. And this is the same for any sensor, which will have basically a scale factor or a sensitivity curve, which is sinusoidal. So we usually try to use some techniques by changing the frequency of the lasers to really ensure that even when the frequency is changing, we are always where the system is the most sensitive. So there are three aspects.
Another question on the chat: how good should be the classical accelerometer to use in each experiment that you talked about?
So again, this is a very, very interesting question. And so just maybe to answer, this is today what can limit us. So again, so the classical accelerometer will record the acceleration. It has some noise, and the noise leads to an uncertainty of the phase measurement. So if this uncertainty is bigger, basically, than the phase difference that would correspond to a minimum and a maximum of the fringe here, then you will not be able to resolve that anymore. And basically, we want even much better than that. So it's hard to quote what is the sensitivity you need, because it really depends on what type of experiments you want to do. If you want to do, for example, a gravimeter, it's slightly different. Well, here you need to remove some noise, and you can do it with very good seismometer. And in that case, you can go down to microgal, so 10 to the minus 9G, without any very strong limitation. If you want to use now the accelerometer on the full band with high frequencies, for example, in a plane, up to now, we know that below something which is more like 10 to the minus 6 G, so it's like 3 orders of magnitude larger than what you can get on the ground, you start to be limited by the accelerometer and the classical accelerometer you can use.
Okay. So I have seen that there is these other proposals to look at gravitational waves using clocks rather than gravimeters.
Yeah.
Can you comment on the comparison between these two?
Well, it's at that level, it's almost well, they are in some sense they are very similar in the sense that you know, if I say that really what happens when I have a gravitational wave passing by is I have two points that are defining as inertial references, and then I want to measure the time the light goes from one place to the other. So the clock will measure the time, and we'll measure the phase, so which is basically the integral of the, well, the time is basically sorry, the phase is related to the time with respect to the number of oscillation you had. So there is a link between them. So the sensitivity curve is not exactly the same, and the concept is not exactly the same. And so far, I think it's nice to pursue both aspects, but it's very, very close with respect to what you are measuring.
Okay, thank you. And the detector, this MEGA detector that has this great sensibility, can it detect an earthquake because of its gravitational signal rather than the seismic signal?
So it's, I would say, well, I will answer yes. And why is that? Then again, you really have to look precisely at what you want to measure in order to give a more precise answer. And this is exactly what I said is, so basically what we hope is that we won't see any seismic noise, because we want to be isolated from the seismic noise as much as we can. But any gravitational forces arising from the masses around your system will actually affect the MEGA antenna, or affect one cloud with respect to the other. So if you have and this is what, if you have a variation of this mass around your system, that's basically what's called gravity gradient noise or Newtonian noise for gravitational wave detection. You will see a signature which does not come from the vibrations, but really from the mass fluctuation. And basically, that's what will happen if you have an earthquake. If you have a seismic wave passing by, and that modifies the position of the mass or shakes the position of the mass, then you will see the signature with the signal. So yes, is the answer.
They're asking also on the chat whether you have any postdoc opportunities in your group.
Please apply. Yes, we have from time to time. We have postdoc opportunities. Now we're looking for postdocs in many of the projects. I mean, maybe not precisely MIGA or maybe not precisely this, but yes, please do apply, and we have many possibilities.
Okay, thank you very much.
That was an easy answer.
So I don't see more questions on the chat. So then I guess we'll stop here, and thank you again for the extraordinary talk. That was really, really interesting. And we thank you very much for accepting our invitation.
Thank you for the invitation, and a happy birthday for your institute then again.
Thank you very much. Okay.
And with pleasure for next time.
Sounds good. Sounds good. Hopefully next time we can have it live.
Yes, hopefully, yes.
Thank you very much.
Thank you very much. Bye-bye.